Welcome back. Now we're going to talk about chapters 19 and 20, confidence intervals and hypothesis testing when we're dealing with one sample and we're looking at a percent or a proportion of that one group. So chapter 19 is doing confidence intervals and chapter 20 is doing hypothesis testing. So we're going to try one of each. So first, and this is the same handout, in a certain county, 12 of 96 people called for jury duty are Hispanic. Estimate the percent of all people called for jury duty that are Hispanic. So think of the 4 questions we need before we can decide what formula it is that we need. First, what kind of data do we have, categorical or quantitative? This is categorical. Is the person called for jury duty Hispanic or not Hispanic? So it's categorical data. Do we need to compute sample size? No, we don't. We've got 96 in our sample. We already have a sample size, so we don't need one. We're not asking how many people do we need to call for jury duty to figure this out. We already have 96 people in our hand. Number of samples, we have one group of people called for jury duty. One group, one sample. And then finally, do we want confidence interval or hypothesis testing? Well, we want to estimate the percent of all people who are called for jury duty that are Hispanic. We want to know what that thing is. Where, in what interval will we find the percent of all people called for jury duty that are Hispanic? So we want confidence interval. So we want to go to our formula sheet. We'll deal with proportions or percents. We have one sample, and we want confidence intervals, the +4 confidence interval. So there's our formula right there. Here you have some extra information. The sample percent is tweaked. We add 2 to the top and 4 to the bottom. That is because if we don't tweak it, our level of confidence is fluctuating. And a simple tweak just keeps that level of confidence up where we want it. And then our new sample size is the old one +4. So let's try one. So our formula is that right there, where our sample percent is tweaked. We're going to add 2 to the top and 4 to the bottom. So our original sample was 12 out of 96 people are Hispanic that were called for jury duty. So we have 12 out of 96, but we're going to add 2 to the top and 4 to the bottom. So we get 14 out of 100, or 14% in our sample are Hispanic. That's what we are starting out with. That's our best guess at the truth in the population. But we know that if we took a different sample, we'd get a different percent. And so that's why we have to add and subtract the margin of error. The margin of error gives us some idea of how close that 14% is to what we really want to know, the true percent of all jurors called that are Hispanic. So how close is this sample percent to what it is we really want to know, the percent in the population of jurors that are Hispanic? So we have our sample percent. Now we want 95% confidence. So for 95% confidence, we're going to use a Z of 1.96. And now we have everything we need. So let's just get to those numbers. And so we have 0.14 plus or minus 1.96 times the square root of 0.14 times 1 minus 0.14 over 100. Our new sample size, 96 plus 4. So 0.14 plus or minus, multiply this by this, divide by 100, take the square root, multiply by 1.96, and we get 0.068. So this 0.14 is p hat. That's the sample percent. This is the margin of error, is how close we think that 14% is to the true percent. So we subtract first to get the lower end of the bound, and we get 0.072, and we add, and we get 0.208. So there's our confidence interval. To interpret that confidence interval, we ask for three things. We're looking for three things. One is, what is our level of confidence? So are we 90% confident, 95% confident, 99% confident? In this case, we are 95% confident that this interval catches the truth. We're never completely confident. We never prove anything with statistics, but we're pretty sure, assuming we have a simple random sample, that we have caught the truth, 95% sure. So we are 95% confident that then the next thing we need is the range. We are 95% confident that 7.2% to 20.8% of, then the third thing we need is of what? Of what? Of the population, of this sample, of future samples. Well, remember, inference is always about the population. So in this case, we are 95% confident that 7.2 to 20.8% of all people called for jury duty are Hispanic. The percent of the entire population that's Hispanic is somewhere in this range. Now, according to the census, 19% of people in the county are Hispanic. Does this confidence interval suggest that the jury is representative of the county, at least in terms of the percent of Hispanics? So what do you think? Is it reasonable to claim that 19% of jurors are Hispanic? Well, our confidence interval goes from 7.2 to 20.8%. So any number in there is a reasonable claim for the true percent of Hispanics that are called for jury duty. So since 19% is in there, 19% is a completely and totally reasonable claim for the percent of jurors called that are Hispanic. So yes, because 19% is in our confidence interval, it's a perfectly reasonable claim for the true percent of Hispanics called for jury duty. So yes, totally reasonable. That's confidence intervals. And now we'll move on to hypothesis testing, and then we'll go on to chapter 22 in the third video. So here's the second part of this same video. So we're going to try hypothesis testing with the same data. We're answering a yes/no question. Are 19% of people called for jury duty Hispanic? So this is chapter 20. So with hypothesis testing, we need a four-step procedure. We need hypotheses, we need a test statistic, we need a p-value, and then we'll draw our conclusion. The hypotheses are always a claim about what's true in the population. We have no need to make a claim about the sample because we already know what we've got, right? About 12.5% or 14%, depending on whether you do the +4 procedure, we're Hispanic. So we need to make a claim about what's true in the population. We're wondering if the percent among jurors that are Hispanic is 19%. So that's our claim. And we wonder if it's that or basically different from that. So our null is that the percent is 19% and the alternate is that it's something different from that. Then we need our test statistic. So we're dealing with percents. We have one group of people called for jury duty. We want hypothesis testing. So there's our formula right there. Sample percent without the +4, it's just a straight sample percent, minus the hypothesized percent over the square root of that thing. So we're just going to write that down and find a few numbers. So z equals p hat minus p0 So our sample percent, the real one, is 12 out of 96. We don't tweak it for hypothesis testing. So that's 0.125. And the hypothesized percent is 19%. And so we have everything we need. So z is 0.125 minus 0.19 over the square root of 0.19 times 1 minus that over 96. So our z statistic is minus 1.63. So what that says, remember, z statistic is the number of standard deviations we are away from the mean. So in this case, our 12.5%, our sample percent, is 1.63 standard deviations away from what we hypothesized. So you have some idea from chapter 6 how often we would see such a thing. So for p-value, our alternate is not equal to. That's two-sided. So we're going to go to table Z, and we have to look at both sides. Both sides. We have to look above Z equals 1.63 and below Z equals minus 1.63. So we're going to go to table Z and find this piece and this piece. Well, let's look at the lower one first. That's the only one we need to look at. So we find minus 1.63, and the probability of getting something lower than that is 0.0516. 0.0516. So this is 0.0516. This is 0.0516. So the total p-value is 0.0516 times 2 is 0.1032. There's our p-value. Now to draw conclusions, we have to compare that to an alpha. We have to choose some cutoff. If we would see it that rarely just by chance, then we don't think that our null hypothesis is probably true. If we'd see a sample like this so rarely just by chance, if the null is true, then we think the null is not true. But in this case, we would see samples like this, a sample like this, more than 10% of the time if the null hypothesis is true. We would see a sample like this regularly if the null is true. So if alpha is 0.01, the p-value is greater than alpha. If alpha is 0.05, p is greater than alpha. If alpha is 0.10, in all these cases, p is greater than alpha. So in all the cases, we would accept the null hypothesis that there are 19% of Hispanics among these jurors. Okay? So no matter what our alpha is in this case, we're going to have a p-value that's greater than it. So in all these cases, we would accept the null hypothesis. It is not statistically significant because we are accepting the null hypothesis. So in all these cases, we would believe that the percent of Hispanics among people called for jury duty is 19%. At least we don't have enough evidence to say it's not. Now, what would the alternate have been if we wondered if the percent of Hispanics called for jury duty was less than 19%? If we wondered if it was less than, then our null hypothesis would be p is less than 19%. But if we thought this was our alternate, wondered if it was less than, then our p-value would be just this piece right here, 0.0516. And now 0.0516 is still greater than this, it's greater than this, but it's less than this. 0.0516 is less than 0.10. So this alpha, 0.10, would be the only one for which we had statistically significant results. So what would the alternate be if we wondered if the percent of Hispanics called for jury duty was less than 19%? Well, p is less than 0.19. Our p-value is 0.0516. At what alpha would that p-value be statistically significant? For what alpha is the p-value less than or equal to alpha? Only alpha equal to 0.10. It would be not statistically significant for 0.05 or 0.01. So that is what we do when we have one sample, confidence intervals and hypothesis testing, chapters 19 and chapter 20. Now we'll go on in the next video to chapter 22, what happens when we have two groups compared on a percent.